Whether a ground fault circuit interrupter, or GFCI, is needed for a wired outlet depends on several factors. Location is a primary consideration. GFCIs are typically required in bathrooms, kitchens, garages, and outdoor areas due to the presence of water and the increased potential for electrical hazards. In locations such as laundry rooms, crawl spaces, and attics, GFCIs are generally not mandated, but their use is often recommended to provide an extra layer of protection. For other areas, such as living rooms, bedrooms, or other dry spaces, GFCIs are not typically a requirement. Specific electrical codes also dictate GFCI requirements. The National Electrical Code, or NEC, establishes baseline requirements for GFCI protection in the locations previously mentioned. It is critical to be aware that local building codes may impose additional or more stringent requirements for GFCI protection beyond what is outlined in the NEC. Even in situations where GFCI protection is not mandated by code, it is generally a good practice to install GFCIs in areas where there is an elevated risk of electrical shock, such as near water sources or in workshops. In summary, if the wired outlet is situated in a bathroom, kitchen, garage, or outdoor location, it is generally required to have GFCI protection. In other areas, it is not explicitly required but may be recommended to enhance safety. It is always essential to consult your local building codes to ascertain the specific requirements applicable to your location. Firstly, understand the function of a GFCI. A GFCI constantly monitors the current flowing through a circuit. If it detects any imbalance, indicating that current is leaking to ground, it quickly trips the circuit, cutting off the power and preventing electrical shock. This is particularly important in wet locations, where the risk of electrical shock is much higher. Secondly, consider the age of the wiring. Older homes may not have the same level of grounding as newer homes, which can increase the risk of electrical shock. In such cases, even if not strictly required by code, adding GFCI protection can significantly improve safety. Thirdly, think about the types of appliances that will be used with the outlet. If the outlet will be used to power appliances that are likely to come into contact with water, such as hair dryers or electric razors in a bathroom, a GFCI is highly recommended. Fourthly, be aware of the specific requirements for different types of outlets. For example, the NEC has specific rules for receptacles located within a certain distance of a sink. Fifthly, ensure proper installation. A GFCI outlet must be correctly wired to function properly. If you are not comfortable working with electrical wiring, it is best to hire a qualified electrician to install the GFCI. Sixthly, test the GFCI regularly. GFCI outlets have a test button that should be pressed periodically to ensure that the outlet is functioning correctly. If the outlet does not trip when the test button is pressed, it should be replaced. Seventhly, document the installation. Keep a record of where GFCI outlets are installed in a home, as well as the date of installation. This can be helpful for future maintenance and repairs. Eighthly, consider using a GFCI circuit breaker instead of a GFCI outlet. A GFCI circuit breaker provides protection for the entire circuit rather than just the outlet itself. Ninthly, be aware of the limitations of GFCI protection. A GFCI will not protect against overload or short circuits. It is designed to protect against ground faults, which are a specific type of electrical hazard. Tenthly, stay up to date with the latest electrical codes. Electrical codes are updated periodically to reflect new technologies and best practices. It is important to stay informed of any changes to the codes that may affect your home. The NEC, specifically Section 210.8, details the requirements for GFCI protection. The requirements are not just for dwellings but also for commercial and industrial locations. For dwelling units, GFCI protection is required for 125 volt through 250 volt receptacles supplied by single-phase circuits rated 150 volts or less to ground in specific locations. These locations include bathrooms, garages, grade-level portions of unfinished or finished basements, kitchens, and areas within 6 feet of the outside edge of a sink. Additionally, GFCI protection is required for outdoor receptacles, crawl spaces at or below grade level, laundry areas, boathouses, and all 120V through 240V receptacles installed in dwelling unit hallways. The NEC also provides exceptions to these requirements. For example, a receptacle supplying only a fire alarm system is not required to have GFCI protection. Furthermore, a receptacle behind a refrigerator or freezer is not required to have GFCI protection if it is dedicated to the appliance and readily accessible. For commercial and industrial locations, GFCI protection is required for 125V through 250V receptacles supplied by single-phase circuits rated 150V or less to ground in specific locations. These locations include bathrooms, kitchens, rooftops, and outdoor locations. Additionally, GFCI protection is required for receptacles within 6 feet of the outside edge of a sink, as well as for receptacles in damp or wet locations. The NEC also provides exceptions to these requirements for commercial and industrial locations. For example, a receptacle supplying only a fire alarm system is not required to have GFCI protection. Additionally, a receptacle that is part of a listed industrial control panel is not required to have GFCI protection. It is important to note that the NEC is not law. It is a set of recommendations that are developed by experts in the electrical industry. However, many local jurisdictions adopt the NEC as their electrical code, making it legally binding. It is also important to remember that the NEC is a minimum standard. Local jurisdictions may have more stringent requirements. It is always best to check with your local building department to determine the specific requirements for your area. When selecting a GFCI outlet or circuit breaker, it is important to choose one that is listed by a recognized testing laboratory, such as Underwriters Laboratories, or all. This ensures that the device has been tested and meets safety standards. It is also important to select a GFCI that is rated for the voltage and current of the circuit it will be protecting. GFCIs are available in various ratings, such as 15 amps and 20 amps. It is crucial to choose a GFCI with a rating that matches the circuit's rating to ensure proper protection. The installation of a GFCI outlet or circuit breaker is a relatively straightforward process, but it is important to follow the manufacturer's instructions carefully. Before starting any electrical work, be sure to turn off the power to the circuit at the circuit breaker. It is also a good idea to use a voltage tester to verify that the power is off before touching any wires. When wiring a GFCI outlet, it is important to connect the wires to the correct terminals. The outlet will have markings indicating the line and load terminals. The line wires are the wires that bring power to the outlet, while the load wires are the wires that continue the circuit to other outlets or devices. If you are unsure which wires are the line wires and which are the load wires, you can use a voltage tester to check. Once the wires are connected, carefully tuck them back into the electrical box and screw the outlet into place. After installing the GFCI, it is important to test it to make sure it is working properly. Most GFCIs have a test button that can be pressed to simulate a ground fault. When the test button is pressed, the GFCI should trip, cutting off the power to the outlet. If the GFCI does not trip, it is not working properly and should be replaced. Regular testing of GFCI outlets is essential to ensure that they are providing the intended protection. It is recommended to test GFCIs at least once a month. GFCIs are an important safety device that can help to prevent electrical shock. By understanding the requirements for GFCI protection and installing and testing GFCIs properly, you can help to keep yourself and your family safe from electrical hazards. The technology behind GFCIs relies on the principle of monitoring the current balance between the hot and neutral conductors in a circuit. Under normal operating conditions, the current flowing through the hot conductor should be equal to the current returning through the neutral conductor. A GFCI continuously monitors this balance. If there is a difference of more than a few milliamperes between the hot and neutral currents, it indicates that some current is leaking to ground, potentially through a person who is touching a live wire. When the GFCI detects this imbalance, it quickly trips the circuit, typically within 20 to 30 milliseconds, cutting off the power and preventing a sustained electrical shock. The tripping mechanism in a GFCI typically involves a differential transformer that senses the current imbalance. The transformer's output is connected to a solid-state circuit that controls a relay or circuit breaker. When the imbalance exceeds the threshold, the solid-state circuit activates the relay or circuit breaker, interrupting the current flow. GFCIs are designed to protect against ground faults, which are a specific type of electrical hazard. They do not protect against overloads or short circuits. Overloads occur when too much current is flowing through a circuit, typically due to too many devices being plugged into the circuit. Short circuits occur when there is a direct connection between the hot and neutral conductors, bypassing the intended load. Overloads and short circuits can cause wires to overheat and potentially start a fire. Circuit breakers and fuses are designed to protect against overloads and short circuits. These devices trip or blow when the current exceeds a certain level, cutting off the power to the circuit. GFCIs and circuit breakers work together to provide comprehensive electrical protection. GFCIs protect against ground faults, while circuit breakers protect against overloads and short circuits. It is important to have both types of protection in your home to ensure electrical safety. When installing a GFCI, it is important to follow the manufacturer's instructions carefully. The instructions will provide detailed information on how to wire the GFCI correctly. It is also important to test the GFCI after installation to ensure that it is working properly. The test button on the GFCI simulates a ground fault, and the GFCI should trip when the button is pressed. If the GFCI does not trip, it is not working properly and should be replaced. Regular testing of GFCIs is essential to ensure that they are providing the intended protection. It is recommended to test GFCIs at least once a month. GFCIs are an important safety device that can help to prevent electrical shock. By understanding how GFCIs work and installing and testing them properly, you can help to keep yourself and your family safe from electrical hazards. It is also essential to be aware of the limitations of GFCI protection. GFCIs are designed to protect against ground faults, but they do not protect against all electrical hazards. For example, GFCIs will not protect against electric shock if a person comes into contact with both the hot and neutral wires simultaneously. In this scenario, there is no current leakage to ground, so the GFCI will not trip. Therefore, it is important to always exercise caution when working with electricity, even when GFCI protection is in place. Always turn off the power to the circuit before working on any electrical components. Use insulated tools and wear appropriate safety gear, such as rubber gloves and eye protection. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work. The evolution of GFCI technology has led to more sophisticated and reliable devices. Early GFCIs were often prone to nuisance tripping, which could be frustrating for homeowners. However, modern GFCIs are much more resistant to nuisance tripping due to improved filtering and signal processing techniques. Another advancement in GFCI technology is the development of self-testing GFCIs. These devices automatically test themselves periodically to ensure that they are functioning properly. If a self-testing GFCI detects a problem, it will typically indicate the problem with a visual or audible alarm. Self-testing GFCIs provide an extra layer of assurance that the GFCI is providing the intended protection. In addition to GFCI outlets and circuit breakers, there are also portable GFCIs available. These devices can be plugged into a standard outlet and provide GFCI protection for any devices plugged into the portable GFCI. Portable GFCIs are useful for temporary applications, such as construction sites or outdoor events. When choosing a GFCI, it is important to consider the environment in which it will be used. GFCIs are available in various types, including indoor, outdoor, and weather-resistant models. Outdoor and weather-resistant GFCIs are designed to withstand exposure to the elements, such as rain, snow, and sunlight. It is also important to choose a GFCI that is rated for the appropriate voltage and current. GFCIs are available in various ratings, such as 15 amps, 20 amps, and 30 amps. It is essential to choose a GFCI with a rating that matches the circuit's rating to ensure proper protection. The cost of GFCI outlets and circuit breakers has decreased significantly over the years, making them more accessible to homeowners. While the initial cost of a GFCI may be slightly higher than a standard outlet or circuit breaker, the added safety and protection they provide make them a worthwhile investment. In addition to protecting against electrical shock, GFCIs can also help to prevent damage to electrical appliances and equipment. Ground faults can cause excessive current to flow through appliances, which can damage sensitive electronic components. By quickly interrupting the current flow, GFCIs can help to prevent this type of damage. The installation of GFCIs is an important part of a comprehensive electrical safety plan. It is also important to have a properly grounded electrical system which provides a safe path for fault current to flow back to the source. A ground fault can occur when there is an unintentional electrical path between a live wire and ground. This can happen if a wire becomes frayed or damaged, or if a metal object comes into contact with a live wire. If a person touches a metal object that is in contact with a live wire, they can receive an electrical shock. A properly grounded electrical system provides a low resistance path for fault current to flow back to the source, which can trip a circuit breaker or GFCI and cut off the power before a person is injured. Grounding is typically achieved by connecting the metal enclosures of electrical equipment and appliances to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode provides a connection to the earth, which helps to stabilize the voltage and provide a safe path for fault current. It is important to have a qualified electrician inspect your electrical system to ensure that it is properly grounded. The electrician can also perform tests to verify the integrity of the grounding system. Regular maintenance of your electrical system is also essential to ensure safety. This includes inspecting wiring for damage, replacing worn or frayed cords, and testing GFCI outlets and circuit breakers. By taking these precautions, you can help to prevent electrical hazards and keep your home safe. The NEC specifies the requirements for grounding and bonding in electrical systems. Bonding refers to the process of connecting together all metal parts of an electrical system to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. The NEC requires that all metal enclosures of electrical equipment and appliances be bonded together. This includes metal conduit, metal junction boxes, and metal appliance housings. Bonding is typically achieved by using bonding jumpers, which are short lengths of wire that connect the metal parts together. The NEC also requires that the grounding electrode conductor be bonded to the neutral conductor at the service entrance. This connection helps to stabilize the voltage and provide a low impedance path for fault current. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. It is important to follow the NEC requirements for grounding and bonding to ensure the safety of your electrical system. Improper grounding and bonding can increase the risk of electrical shock and fire. The role of arc fault circuit interrupters, or RFCIs, in electrical safety is also important. RFCIs are designed to protect against arc faults, which are a type of electrical fault that can cause fires. Arc faults occur when there is an unintentional electrical discharge between two conductors. This can happen if wires become frayed or damaged, or if there is a loose connection. Arc faults can generate high temperatures that can ignite nearby materials, such as wood or paper. RFCIs are designed to detect arc faults and quickly trip the circuit, cutting off the power before a fire can start. RFCIs use sophisticated electronic circuitry to detect the unique characteristics of arc faults. They can distinguish between normal arcing, such as that which occurs when a switch is turned on or off, and dangerous arcing that indicates a fault. The NEC requires RFCIs in many locations in homes, including bedrooms, living rooms, and dining rooms. RFCIs are typically installed in the circuit breaker panel. It is important to choose RFCIs that are listed by a recognized testing laboratory such as UL. This ensures that the devices have been tested and meet safety standards. RFCIs and GFCIs provide complementary protection against electrical hazards. GFCIs protect against ground faults, while GFCIs protect against arc faults. By having both types of protection in your home, you can significantly reduce the risk of electrical shock and fire.